All right, so this is lesson 1.5. The first thing that we really want to get our head around here is the definition of a theorem. So a theorem, we've talked about before what a postulate is, right? And a postulate was something that we accepted as being true without proving it. So like the linear pair postulate, we just accept the fact that when two angles look like they do when they're a linear pair, they're always going to be supplementary. We don't have to prove it, we're just accepting that. That's a postulate. A theorem is something that you actually can prove. You can write a two-column proof or a flowchart proof. You can write a formal proof to prove that fact, and then it's a theorem. So theoretically, things kind of start out as conjectures, like, it seems like this is always going to be true, you know? And then somebody writes a formal proof about it, and that's how it kind of gets promoted to being a theorem. Okay? So in this class, every time we come across a theorem in the book, right, we can write the formal proof of that theorem. I mean, theoretically, we should do that every time before we actually use it in a proof. We don't have time to prove every single theorem. We'd be here proving theorems all day. So we don't prove formally every single theorem we learn, but several of them we do. And part of, the understanding of geometry is to understand that everything starts from very basic facts. A point, a line, a plane. Very basic facts, postulates, and we can use those things and all the properties, and we can prove formally all of these other theorems, which then help us prove more theorems. And it just goes on and on. Okay, so that's kind of an important thing to understand about geometry in general. I forgot to revise this one piece of it because I did already teach you the vertical angles theorem. Last year we hadn't learned that quite yet, so that's why it says we haven't learned it yet. But the vertical angles theorem we did learn, and it says that vertical angles are congruent. Okay, let's write this as a conditional. How could you write vertical angles are congruent as a conditional? Yep. Okay, let's say if they, right, because they have to come in a pair, if they are vertical angles, then they are congruent. So when you take a theorem and you write it as a conditional, an if-then statement, like I said, we can formally prove every theorem. So when we take the if-then statement, the hypothesis becomes our given, and the conclusion becomes our proof. And then we can write a proof of that theorem. Okay? So what's the hypothesis? Hypothesis. That was good recording. Yep. Good. They are vertical angles. So that's going to become our given. So if you look at the proof down here, down below, the proof of the vertical angles theorem, we have a specific diagram, but our given is that angle 2 and angle 4 are vertical angles. Angle 2 and angle 4 are vertical angles. So see how the given is just stating that two angles are vertical angles. That's it. We're just stating that they are vertical angles. What is the conclusion of this if-then statement? Yep. Good. They are congruent. So that becomes what you're trying to prove. We're proving that angle 4 is congruent to angle 2. Okay. Now, if I gave you this proof 5 minutes ago, you would say this is a two-step proof. You just like, okay, they're vertical, so they're congruent. And my reason is the vertical angle theorem, right? Okay. That's going to be true and good going forward, but this is the proof of that theorem. We cannot use that theorem to prove that theorem. It's kind of like when you write a definition of something. You can't like use the word to define the word. You know what I'm saying? Right? So you can't use the theorem to prove the theorem. You have to prove this fact some other way using other things that we know. Okay? So that's important to remember. Some proofs are proofs of theorems. Some proofs are not. Okay? But if it is a proof of a theorem, you have to make sure you're not using the theorem to prove it. Okay. So let's start with our given. Angle 2 and angle 4 are vertical angles. That's nice. You could do this as a 2-column proof if you want. But now I'm going to look at my diagram. Is there anything else we can mention that might be useful for us in that diagram? Yeah. Okay, 1 and 3 are vertical angles, that's true, but since we don't have a theorem about vertical angles, that particular fact isn't going to help us, because it would be really nice if we could say they were congruent by the vertical angles theorem, but we can't use that theorem. So let's find another relationship. Gabe? 1 and 2 are supplementary. Why? Okay, makes them a linear pair. So the linear pair postulate says 1 and 2 are supplementary. Good. What else? Yep. True. 3 and 4 are also linear pair and supplementary. What else? So we have 1 and 2. We have 3 and 4. Are there other linear pairs? Okay, 1 and 4 and 2 and 3. So it's going to be helpful for us to use the same angle twice. In other words, angle 1 and 2 are supplementary, and angle 2 and 4 are supplementary. I'm sorry, 1 and 4 are supplementary. So we're using angle 1 to relate to 2 and 4 because we're trying to prove that 2 and 4 are the same. So if we can show that they have the same relationship to something else, it's going to help us. Okay, so 1 and 2 are supplementary, 1 and 4 are supplementary by the linear pair postulate. What would be the step that leads logically from that statement? Claire? Right? That's always the next logical step from linear pair postulate is to then write equations. What is the reason there? Definition of Riley? Supplementary. Now what might you do? Yep, Colin. Good. So we're going to rewrite this equation substituting measure of angle 1 plus measure of angle 4 in for the 180. So in other words, if two things are both equal to the same number, you can set them equal to each other by substitution. Now what? What could we do to both sides of this equation? What could we do to both sides? Yeah, Doug? Good, and you get measure of angle 2 equals the measure of angle 4 by subtraction. Now can we say angle 4 is congruent to angle 2? Angle 4 is congruent to angle 2. What's the reason? If they're equal, good. If they're equal, we can say they're congruent. This definition of congruent works both ways, right? If you have a statement that says they're congruent, then you can say they're equal by definition of congruent. But this case, we have that they're equal, and we can state that they're congruent by definition of congruent. Just shows the properties that you're used to, reflexive, transitive, these two properties, we know them as properties of equality, right? We talked about reflexive property of equality, 2 equals 2, measure of angle A equals measure of angle A. And transitive property we used in equations. Now we're learning the property of congruence. It's the same thing except without an equal sign now, it's with a congruent sign. Right? So the reflexive property of congruence says that A is congruent to A. Right? And the transitive property of congruence says if A is congruent to B and B is congruent to C, then A is congruent to C. Right. And this is just reiterating what we just talked about. Definition of congruence can really be used both ways. If you know things are congruent, you can state that they're equal. If you know things are equal, you can state that they're congruent. Your reason in both cases is definition of congruence. Okay, so this is a proof using the vertical angles theorem. Okay, so we can use the vertical angles in this diagram. 1 and 3, 2 and 4. They're congruent to each other. Now, when we used vertical angles theorem in proofs before, usually our next step was to say the measures are equal, right? Because we were going to put them into an equation somewhere. So we had to get the measures equal. We don't have to do that here. Because look at what we're trying to prove. We're trying to prove congruence. So we have everything in congruence. We don't want to put it into equals. We're just going to have to switch it back to congruence later. So if it's all in congruence, you don't have to go that route to saying the measures are equal. Now, this is kind of where we can use that transitive bucket. Did we talk about the transitive bucket? Right? If 1 is congruent to 4, I'm going to put those both in this bucket. Now I'm going to come over here and it says 1 is congruent to 3. Well, 1's already in my bucket, and so 3 can join the 1 because they're both congruent. And then this one, 4 is congruent to 2, so 4 is in my bucket already, so I could put 2 in the bucket. So now any of these inside here can be stated congruent to each other, which is good news for us because we're trying to prove that angle 2 is congruent to angle 3. What kind of a bucket was this? A transitive bucket. So this is the transitive property. And this time, it's not a property of equality, P-O-E, it's a property of congruence, P-O-C. Property of congruence. So here we do need an arrow coming from our given, because we put 1 and 4 into our transitive bucket, and we put 1 and 3 and 4 and 2 into our transitive bucket. So we really used both of those statements to make our 2 congruent to 3 conclusion. So right angles theorem says if two angles are right angles, then they are congruent. So our if of our proof of this theorem is going to be that two angles are right angles. And our then becomes our proof that those two angles are congruent. So here's our proof of the theorem. Angle 1 is a right angle, angle 2 is a right angle. Prove that angle 1 is congruent to angle 2. Now, remember, these could be done as two-column proofs, but I'm going to stick with flowchart for now. So what conclusion could we make from this fact? Angle 1 is a right angle. So what do you know about it? Yeah, so from this box, we're just going to say the measure of angle 1 equals 90, and the measure of angle 2 equals 90. What do you suppose that reason is? Emmett? Good, definition of right angle. We just knew what a right angle was. Now, when you have two things that are equal to the same number, what can you do with them? Set them equal to each other by substitution. So angle 1 equals the measure of angle 2 by substitution. And therefore, angle 1 is congruent to angle 2 by what reason? If their measures are equal, you could say they're congruent. Definition of congruent. We drew angle B supplementary to A, and angle C supplementary to A. They're both 120 degrees, so if two angles are both supplementary to the same angle, then the two angles are, I heard you guys say it, congruent. Right? They're both 120. So they have the same measure, makes them congruent. So this theorem is actually called the congruent supplements theorem. Now, notice this little piece that's in parentheses here. It says if two angles are supplements of the same angle or of congruent angles. So just real quickly, pretend this is angle D, and it's also 60. If I say that A and D are congruent, I establish that as a fact. Angle A and D are congruent. They're both 60. And if I said draw angle B supplementary to A, you would make it 120. And then what if I said draw angle C supplementary to D? It would still be 120, right? So if two angles are supplements of the same angle or of two angles that are congruent to each other, then the two new angles are congruent. Okay, so we worked through that already. This was just 120 and 120, congruent. All right, so proof of the congruent supplements theorem. I just want to show the people watching the video the answer to our proof. Okay, they can pause it if they want that longer. So this is the same idea. Two angles that are complements of the same angle. So we could go through this process again. Draw angle B that's complementary to angle A. All right, so draw angle B over here. How many degrees would angle B have to be if it's complementary to A? Okay, 30 degrees. Now I'm going to draw angle C that's also complementary to angle A. How many degrees is that going to be? 30. So they're both 30 degrees. That makes them congruent to each other. So this theorem is called the congruent complements theorem. And it says pretty much the same thing as the congruent supplements theorem, except with complementary angles instead. So two angles, complements of the same angle. Again, there's this little dot, dot, dot. Or of congruent angles, right? Then the two angles are congruent. Okay, so this proof, actually, the proof of the theorem, is using that little dot, dot, dot part. It's saying that 2 and 4 are complementary, and 3 and 5 are complementary, and then it's saying, okay, and that says given. And it says angle 4 is congruent to angle 5. So we're going to mark 4 congruent to 5 in our diagram. So this is the one, it's not two angles that are complementary to the same angle. These are two angles that are complementary to congruent angles. So it's important to remember to turn those congruents into equal if you want to subtract one from one side and one from the other side. Or if you're ever substituting, you have to do that as well. Okay. So this is some practice now. So we're doing this proof again, kind of flip-flopping. Keep this as supplementary, change this to supplementary. Now I have two statements where I'm saying that two angles are supplementary to angle 3. One is supplementary to angle 3, 2 is supplementary to angle 3. So guess what? We can go straight to a statement saying 1 is congruent to 2. See how many steps we eliminated? Two angles are both supplementary to the same angle. That means they're congruent to each other. Our reason here is congruent supplements theorem.